It is 1930. A young astronomer named Clyde Tombaugh bends over a blink comparator and watches two photographic plates flicker back and forth under the light. A single dot moves. That dot is Pluto, and for 96 years we decided it was cold, dead, and irrelevant. We were wrong. The James Webb Space Telescope has now done something no instrument in history could. It read the chemistry of what floats above Pluto's surface in infrared wavelengths our eyes cannot see. And what it found rewrites the story of where life is allowed to exist. Pluto has organic molecules drifting in its haze. It has mountains of ice that should not exist. It may have liquid water beneath its frozen shell, billions of miles from the sun. The edge of the solar system is not what we thought. If this journey is the kind of thing that makes you see the universe differently, we would be genuinely grateful for a like and a subscribe. It means more than you might think. Take a slow breath and let your shoulders drop. In 3, 2, 1, lift off. There is a photograph that changed the history of the solar system, and it looks like almost nothing at all. It is a glass plate developed in the dark room of the Lowell Observatory in Flagstaff, Arizona, on the night of January 23, 1930. The plate is covered in the ghostly white smears of stars, hundreds of them, thousands, each one a sun burning at a distance so enormous that it registers only as a pinpoint of light frozen against the chemical emulsion. Nothing on this photograph looks unusual. Nothing on this photograph looks like a discovery. And that is precisely why what happened next required a machine, a human eye, and 6 weeks of painstaking comparison before anyone noticed what was hiding in the noise. The machine was called a blink comparator. It was a device that allowed an observer to alternate rapidly between two photographic plates taken of the same region of sky on different nights, making the images flicker back and forth in sequence. If a star had moved between the two exposures, it would appear to jump against the fixed background of its neighbors, the way a single raisin in a bowl of poppy seeds would seem to leap if you blinked fast enough. Humanity believed a story about Pluto that turned out to be constructed almost entirely from assumptions stacked on top of other assumptions, stacked on top of a resolution so low that the entire planet fit inside a single blurry pixel. For most of the 20th century, scientists knew almost nothing accurate about Pluto's size, its surface, its atmosphere, or its interior. Early estimates of its mass were wildly inflated because astronomers assumed it was the gravitational anomaly responsible for wobbles they had detected in the orbits of Uranus and Neptune. It was not. Those wobbles were later explained by more careful measurements of the giant planets themselves. Pluto was simply a world that happened to be in the right place at the right time to be found by a young man with a comparator and an extraordinary capacity for patience. When better measurements finally arrived, the news was humbling. Pluto turned out to be smaller than Earth's own moon. Its diameter is approximately 2,377 kilometers, making it roughly 2/3 the width of our lunar companion. Its mass is so small that it would take approximately 450 Plutos to equal the mass of Earth. For decades, this diminutive size was used to justify a certain comfortable indifference. A world this small and this remote, orbiting the Sun at an average distance of 39.5 astronomical units, with an orbital period of approximately 248 Earth years and a surface that never climbs above -375 degrees Fahrenheit, had no plausible mechanism to sustain geological activity. It should have spent whatever internal heat it was born with long before the dinosaurs walked the Earth. By every reasonable expectation derived from planetary science as it existed through the 1990s and into the 2000s, Pluto was a relic, a primordial ice ball drifting in darkness, a frozen record of conditions that existed at the outermost fringes of the collapsing disk of gas and dust that became our solar system 4.5 billion years ago. The Hubble Space Telescope began to peel back the first layer of that comfortable narrative in the years following its 1990 launch. Hubble could not resolve Pluto as a world with detail. The instrument was not designed for targets this small and this close, but it could detect variations in the light reflected from Pluto's surface as the planet rotated, and what those variations told scientists was genuinely puzzling. The surface was not uniform. There were bright regions and dark regions, patches of what appeared to be reflective frost, and patches of something significantly darker and redder. Something on this world was changing over time. In measurements taken years apart, the surface patterns had shifted in ways that could only be explained by active seasonal cycles. Ice sublimating in the weak sunlight and depositing elsewhere, organic compounds darkening under the bombardment of space radiation. It was not the signature of a dead world. It was not the signature of a living one either. It was something more unsettling, a world that was doing something, but doing it just below the threshold of what any instrument of the era could clearly see. That threshold was shattered on July 14, 2015. 11 years ago, NASA's New Horizons spacecraft completed a journey that had taken 9.5 years and covered more than 3 billion miles to arrive in the vicinity of Pluto for a single, irreplaceable flyby, lasting approximately 22 hours of close approach. The spacecraft had no ability to slow down and enter orbit. It was moving too fast, launched on a trajectory that would carry it out beyond the solar system entirely, and the only close-range science it could collect was what its instruments could gather in that brief window before it receded into the dark. What it gathered changed everything. The first images to arrive from New Horizons, even the early, lower-resolution frames transmitted before the full data package was decoded, showed scientists something they were completely unprepared for. Pluto was not a battered, featureless ball of ancient ice. It had mountains, not gentle hills worn down by billions of years of nothing happening, but sharp, angular peaks of water, ice rising approximately 3,500 meters above the surrounding plains, roughly comparable in height to portions of the Rocky Mountains of North America. These mountains were young. The lack of impact craters on their flanks indicated that whatever formed them had done so relatively recently in geological time, within perhaps the last 100 million years. On a world 4.5 billion years old, 100 million years is not ancient. It is practically yesterday. Then came Sputnik Planitia, a vast, roughly heart-shaped plain of nitrogen ice, approximately 1,000 kilometers across, sitting in a depression roughly 2.5 kilometers below the average elevation of Pluto's surface. The plain is not featureless. It is divided into a network of roughly polygonal cells, each 100s of kilometers wide, separated by narrow channels of slightly darker material. The edges of the cells appeared to be in slow but measurable motion. Scientists recognized this pattern immediately. It was convection. The nitrogen ice at the bottom of the basin was being warmed slightly from below, becoming less dense, rising toward the surface in slow columns, spreading outward as it cooled, and then sinking back down at the cell margins in a continuous circulation. Sputnik Planitia was not frozen solid. It was flowing, slowly, imperceptibly from any human timescale, but physically, measurably, actively flowing in response to heat rising from beneath it. And then, appearing above the limb of the planet in image after image as New Horizons looked back at Pluto with the sun behind it, something extraordinary, a blue, layered haze, rising more than 320 kilometers above the surface, spreading out into multiple distinct bands, each one marking a different altitude where organic chemistry was producing a different type of particle. Pluto had more atmosphere than anyone expected, and that atmosphere was doing far more than simply existing. It was building things. Complex, carbon-rich particles were being assembled in the upper reaches of that haze from nitrogen and methane gas by the interaction of solar ultraviolet radiation and energetic particles streaming from the sun. The atmosphere was a chemistry laboratory operating at -375 degrees Fahrenheit in the most remote neighborhood of our solar system, and it had been running continuously for billions of years. Scientists had their first coherent answers. They also had an entirely new set of questions, ones that New Horizons, by the nature of its flyby, could not resolve. What was the source of the heat driving the convection in Sputnik Planitia? What exactly were those haze particles made of? What happened to them when they eventually settled to the surface? Was there anything beneath the ice shell, a liquid layer, a buried ocean, a reservoir of chemistry operating in permanent darkness? The spacecraft had been gone from Pluto's neighborhood for minutes by the time scientists finished absorbing the first images. It would take 16 months to transmit all the data it had collected in those 22 hours of close approach. And even after every byte of that data had been processed and analyzed, the fundamental questions about Pluto's interior and its atmospheric chemistry remained beyond the reach of what New Horizons could determine from a single pass at a relative velocity of more than 36,000 miles per hour. To answer those questions required an instrument that could look at Pluto from much farther away, but with a precision at wavelengths of light that no telescope before it had possessed. It required an observatory that orbited not Pluto, but the Sun, parked at a gravitationally stable point 1.5 million kilometers from Earth, where it could face away from the Sun and look outward into the cold of the solar system with a mirror 6.5 meters across, and instruments designed to read the universe in wavelengths of light completely invisible to human eyes. It required the James Webb Space Telescope. Webb launched on December 25, 2021, and began its science observations following a commissioning period in 2022. Its primary mission goals were focused on the deep universe, on the first galaxies that formed after the Big Bang, on the atmospheres of exoplanets orbiting distant stars, on the formation of stars and planetary systems in nebulae throughout the Milky Way. Pluto was not initially a headline target. It was a solar system body, a nearby world by cosmic standards, and the perception that it had already been well characterized by New Horizons made it seem like something scientists might visit with Webb as a follow-up rather than a priority. That perception proved to be wrong, in ways that the scientific community found both surprising and deeply important. In May of 2023, researchers directed Webb's MIRI instrument, the Mid-Infrared Instrument, a joint contribution from NASA and the European Space Agency, capable of observing light at wavelengths between 5 and 28 micrometers, toward the Pluto-Charon system. No instrument in the history of astronomy had ever observed Pluto in the mid-infrared with anything approaching this sensitivity. What MIRI can do that no previous telescope could do is measure thermal emission, the faint glow of heat radiating from a surface and atmosphere at temperatures that correspond not to visible light, but to wavelengths far beyond the red end of the human visual spectrum. And, within those thermal measurements, it can distinguish between the glow coming from different things, from the surface of Pluto, from the surface of Charon, from the gas in Pluto's atmosphere, and from the solid particles floating in its haze, all simultaneously, and all with enough resolution to separate them into independent signals. The results of those observations were processed and analyzed over the following 2 years, and they began appearing in peer-reviewed journals in 2025. The first major publication, led by Tanguy Bertrand of the Paris Observatory and published in Nature Astronomy in June of 2025, presented thermal light curves measured by MIRI's imaging mode at 4 characteristic wavelengths: 15, 18, 21, and 25 micrometers. By tracking how the thermal emission from the Pluto-Charon system varied as each body rotated through its daily cycle, exposing different terrains and atmospheric cross-sections to the observer, the team was able to reconstruct separate thermal portraits of both Pluto and Charon for the first time in history. No previous instrument had been able to separate their signals at these wavelengths. Webb did it with a precision that transformed previous estimates from rough guesses into calibrated measurements. What emerged from the June 2025 paper was a finding that had been theoretically predicted years earlier by researcher Shi Jiang at the University of California, Santa Cruz, but had never been confirmed by direct observation. Pluto's high-altitude haze is not a passive feature. It is not simply a beautiful blue veil that New Horizons photographed backlit by the sun. It is a thermodynamic engine. The organic particles that make up the haze absorb solar energy and radiate it back to space as infrared light, cooling the atmosphere far more efficiently than the gas molecules alone could accomplish. This process, the haze, acting as a radiative cooler for the upper atmosphere, is what keeps Pluto's atmosphere at its observed temperatures, roughly -333 degrees Fahrenheit at altitude. Remove the haze, and the atmospheric temperature would be significantly different. The haze is not decoration. It is a thermostat. And critically, this thermostat was identified by Webb as producing a phenomenon unlike anything else observed in the solar system. The role that Pluto's haze plays in its climate is genuinely without precedent. It is not like the role of water vapor in Earth's greenhouse warming. It is not like the role of methane in Titan's haze, which functions by different mechanisms and at very different altitudes relative to the atmospheric pressure profile. Pluto sits, as Jiang noted after the publication of the Nature Astronomy paper, in a unique position in the range of planetary atmospheric behavior, where the haze controls the energy balance in ways that models of other worlds do not predict and cannot fully replicate. Webb had found not just new information about Pluto, but evidence that Pluto's climate operates by rules that required scientists to build entirely new frameworks to understand. That would have been enough to justify years of additional research. But there was a second Webb publication from the same observing campaign, this one appearing in Astronomy and Astrophysics in April of 2025. Led by Emmanuel Lelouch and using MIRI's spectroscopic mode, the MRS instrument, to dissect the infrared spectrum of Pluto's atmosphere in unprecedented detail. If the thermal light curve paper told scientists how the haze behaved, the spectroscopy paper told them what it was made of. What Webb read in the spectral fingerprints of Pluto's haze was not simple. The haze contains multiple distinct chemical signatures, organic particles analogous to those found in Titan's atmosphere, built from complex polymers of carbon and nitrogen, hydrocarbon ices, the frozen remnants of simpler carbon-hydrogen molecules that have condensed out of the gas phase at high altitude, and nitrile ices, compounds in which carbon and nitrogen are bonded together in structures that, under the right conditions, can serve as precursors to some of the building blocks of biological chemistry. The spectrum also showed signatures of methane ice and related compounds at the surface, as well as ethylene ice at specific altitudes, adding to the picture of a world whose chemistry is not simple or static, but layered, varied, and actively evolving. None of this was what the old story of Pluto predicted. The old story said, dead world, cold surface, thin atmosphere, nothing interesting happening. The new story, written in the infrared light that only Webb could read, says something far more complicated. It says that Pluto is producing complex organic chemistry in its upper atmosphere, that this chemistry is actively regulating the climate of the world below it, and that the particles produced by this chemistry eventually settle onto the surface and become part of the material record of a world that has been chemically active for the entire age of the solar system. The dot that Clyde Tombaugh found moving in his comparator in 1930 was not a relic. It was not a fossil. It was not finished. It was a world with a chemistry the universe had been running for 4.5 billion years without anyone looking closely enough to notice. The Webb results from 2025 did not answer every question. They answered some with extraordinary precision, and in doing so, they made the ones that remained feel more urgent than ever before. Because embedded in every thermal measurement and every spectral absorption line is the shadow of a deeper question: what is happening beneath the surface, in the dark, in the cold and pressurized interior of this world? What is generating the heat that drives the convection of Sputnik Planitia? What is forcing material upward through the ice shell in ways that have resurfaced terrain within geologically recent time? The answers to those questions are not written in the sky above Pluto. They are written in the rock and ice and chemistry below it. And to understand them, we need to go deeper than any telescope can see. Let us begin with a problem that planetary scientists spent decades pretending was not really a problem. A world that forms at the outer edge of the solar system in the cold zone, where the sun delivers roughly 900 times less energy per square meter than it delivers to Earth, should follow a predictable arc of geological life. It begins hot, compressed by the enormous gravitational energy released during accretion, the process by which small bodies collide and merge again until they form something large enough to be called a world. That initial heat partially melts the interior. Heavier rocky material sinks toward the center. Lighter icy material rises toward the surface. The world differentiates into layers: a rocky core, an icy mantle, an outer shell, and then it begins the long, slow process of cooling. Without an ongoing source of internal heat, without the tidal forces that make moons like Io erupt constantly, or the sheer gravitational weight that keeps the mantles of terrestrial planets fluid for billions of years, a small outer solar system body should simply radiate its birth heat into space and arrive at thermal equilibrium with its surroundings on a time scale far shorter than the age of the solar system. For Pluto, those models predicted geological quiet by roughly 1 to 2 billion years after formation. By the time complex life was arising on Earth, Pluto should have been geologically finished, frozen through, still. A world where nothing happened, because there was nothing left to happen. New Horizons proved those models comprehensively wrong. Not partially wrong, not wrong in the margins, wrong at the center of their most basic prediction. The images returned by the spacecraft showed not one, but multiple lines of geological evidence indicating that Pluto's surface had been actively modified within timescales that are geologically young in some regions, perhaps within the last 100 million years, and in others, possibly ongoing to the present. Understanding how this is possible requires dismantling the assumption one piece at a time, because the answer is not one thing. It is the interaction of several things, each individually insufficient, but together capable of sustaining enough heat and chemical complexity to keep a small, cold world doing things it has no right to be doing. The first source of internal heat is the most universal and the least appreciated. Every rocky body in the solar system contains trace quantities of radioactive isotopes, unstable atomic nuclei that spontaneously decay, releasing energy in the form of heat. The isotopes most relevant to long-term geological heating are uranium-238, thorium-232, and potassium-40. These are long-lived radiogenic heat producers, with half-lives measured in billions of years, meaning they release heat slowly but continuously over timescales that rival or exceed the age of the solar system itself. Every kilogram of rocky material containing these isotopes produces a small but non-zero amount of heat from their decay. And in a body the size of Pluto, estimated to have a rocky core roughly 1,700 kilometers in diameter, representing perhaps 65 to 70% of the planet's total mass, the cumulative contribution of radiogenic heating is not trivial. It is not enough on its own to maintain a liquid ocean beneath Pluto's ice shell at the present day. But it is enough to slow the cooling of the core significantly, to maintain temperatures in the deep interior that are substantially warmer than the surface, and to sustain the temperature gradient between the rock and the ice that drives geological processes in the layers above. Think of it not as a roaring furnace, but as a pilot light, a heat source small enough to seem insignificant, but persistent enough over geological time to change what is possible. The second heat source is one that requires understanding Pluto not as a solitary world, but as part of a binary system. Charon, Pluto's largest moon, is enormous relative to its parent body. With a diameter of roughly 1,212 kilometers, Charon is more than half the diameter of Pluto itself, and their mass ratio, approximately 1:8, makes the Pluto-Charon system the most extreme binary configuration among planetary bodies in the solar system. The two worlds are tidally locked to each other, meaning they always present the same face toward one another, rotating in synchrony as they orbit their common center of mass once every 6.5 Earth days. This tidal lock was reached relatively quickly in geological time, perhaps within the first few 100 million years after the giant impact that is thought to have formed Charon, when a large body struck early Pluto and ejected material that coalesced into a moon. But reaching tidal lock does not eliminate the tidal interaction between two bodies. It reduces it dramatically compared to the churning tidal forces that drive the volcanism on Io, Jupiter's innermost large moon. But the Pluto-Charon tidal interaction has not gone to zero. Models of the tidal thermal evolution of the Pluto-Charon system, including published work by researchers Amirasine Bagheri and colleagues and subsequently developed by others, indicate that even in the tidally locked state, Residual eccentricity in Charon's orbit and slight gravitational flexing of both bodies generate small but non-zero amounts of tidal heating. This tidal contribution to Pluto's internal heat budget is much smaller than the radiogenic contribution, but it adds something, and in a system where every additional degree of internal warmth matters for determining whether a subsurface reservoir remains liquid or freezes solid, small additions can have consequences that scale far beyond their individual magnitude. The third source of heat, and arguably the most conceptually interesting, is not a source in the traditional sense at all. It is an insulating mechanism between Pluto's hypothetical subsurface liquid layer and its outer water ice shell. Models predict the existence of a layer of methane, clathrate hydrates, crystalline solid materials in which molecules of methane gas are physically trapped inside cage-like structures of water, ice, like guests locked inside an ice lattice hotel. Clathrate hydrates are known to exist in the outer solar system, and they have profoundly different thermal properties from ordinary water ice. They conduct heat approximately 5 times less efficiently than solid water ice, meaning that a layer of clathrate hydrates at the base of Pluto's ice shell would act as a thermal blanket, dramatically slowing the rate at which heat from the rocky core escapes outward into the crust and eventually to the surface and into space. The significance of this insulating layer cannot be overstated. If methane clathrate hydrates are present at the ice-rock boundary, they could extend the lifetime of a subsurface liquid layer by hundreds of millions or even billions of years beyond what a simple water ice model would predict. The heat is not stronger, the blanket is thicker. And under that blanket, in the pressurized dark between the rocky core and the ice shell, the conditions for maintaining something liquid, something chemically active, are more favorable than any model without the clathrate layer would suggest. But maintaining liquid water beneath kilometers of ice at Pluto's distance from the Sun requires one more ingredient beyond heat retention. It requires chemistry, and this is where the discovery of ammoniated water ice on Pluto's surface becomes not a curiosity, but a key piece of physical mechanism. Pure water freezes at 32 degrees Fahrenheit at standard pressure. In the interior of Pluto, where pressures increase with depth, the freezing point of water ice shifts somewhat, but remains in a range that is deeply cold by terrestrial standards. An interior that has cooled to temperatures typical of Pluto's mid-crust, somewhere in the range of -150 to -200 degrees Fahrenheit, would freeze a pure water reservoir completely, solid, and seal it from any possibility of geological activity. But water is not the only molecule present in Pluto's interior. Ammonia almost certainly is as well. Ammonia is one of the most abundant nitrogen-containing molecules in the outer solar system, accreted into icy bodies during their formation from the cloud of gas and dust surrounding the young sun. Its presence in Pluto's interior has been inferred from multiple lines of evidence, most compellingly from the detection of ammoniated species, ammonia, in combination with water ice in the spectral data from New Horizons observations of specific terrain types on Pluto's surface. When ammonia and water are mixed together, something chemically important happens. The freezing point of the resulting mixture drops dramatically relative to either pure component. A solution containing roughly 15% ammonia by mass can remain liquid at temperatures as low as -97 degrees Fahrenheit, a depression of more than 129 degrees Fahrenheit, relative to pure water. In the interior of Pluto, where the combination of radiogenic heating, residual tidal heating, and clathrate insulation maintains temperatures in certain regions above this depressed melting point. An ammonia-water mixture does not freeze. It remains liquid. It circulates. It maintains a chemically active interface with the rocky material of the core, and under sufficient pressure, it can find ways to move upward through the overlying ice. This is the mechanism that makes cryovolcanism on Pluto not only possible, but, in the view of the scientists who have studied it most carefully, almost inevitable. When a body of ammonia-water liquid is enclosed within an ice shell sealed by the surrounding crust, and the crust begins to freeze inward from its outer surface as the interior very slowly cools over geological time, the volume of ice increases while the volume of liquid decreases. Ice is less dense than liquid water, meaning it occupies a larger volume per unit mass. The freezing of the enclosing shell drives pressure upward inside the remaining liquid reservoir. That pressure has to go somewhere. And if the surrounding ice contains fractures, faults, or regions of weakness, the kinds of features that tectonic stresses and impact events naturally create in an icy crust over geological time, the liquid finds those weaknesses and follows them upward toward lower pressure, toward the surface. What emerges is not an explosive volcanic eruption in the terrestrial sense. The material is not silicate magma. It is an ammonia-water slush, possibly carrying with it suspended particles of ice, organic compounds from the interior, and other chemical species that have been interacting with the rocky core for billions of years. As it rises through the crust, some of the ammonia may exsolve as gas, providing additional upward buoyancy. When it finally reaches or near the surface, it spreads across the surrounding terrain, covering existing features and creating new ones, hummocky, dome-like structures that look nothing like the impact craters and eroded plains that dominate the surfaces of geologically dead worlds, but that are also distinct from any kind of volcanic structure seen elsewhere in the solar system. The terrain near Right Mons is the most thoroughly studied example of what this process looks like after the fact. Right Mons is a domical structure, approximately 150 kilometers wide, with a central depression roughly 50 kilometers across and scalloped, irregular flanking slopes that suggest the surface above a complex subsurface architecture. Around it, New Horizons imaging revealed a region of hundreds of square kilometers, covered in irregular mounds and hills, all without the sharp features expected from impact, cratering, and all lacking the small craters that would indicate an ancient, unmodified surface. The 2022 study, published in Nature Communications, led by Kelsey Singer of the Southwest Research Institute, and drawing on the full New Horizons imaging and compositional dataset for the Right Mons region, concluded that the most consistent explanation for this terrain is cryovolcanic, resurfacing the extrusion of material from multiple subsurface sources across more than one episode of activity, together producing a landscape that covers a volume of material comparable to large volcanic provinces on other solar system bodies. The total volume of extruded material in the Right Mons region alone is estimated to be comparable to some of the largest volcanic constructs in the inner solar system, which makes it all the more remarkable that it was produced not by a large, geologically vigorous planet, but by a world smaller than Earth's moon. The compositional evidence strengthens this interpretation significantly. Ammoniated species, the spectral signature of ammonia-bearing compounds mixed with water ice, have been detected by New Horizons near the Virgil Fosse region of Pluto, a set of large extensional fractures that are themselves interpreted as evidence of tectonic stress driven by a freezing and expanding interior. Ammonia compounds are vulnerable to destruction by the ultraviolet, radiation, and energetic particle environment at Pluto's surface. They are chemically degraded over timescales shorter than roughly 1 billion years. The fact that they are still detectable at these features means the surfaces exposing them cannot be more than approximately 1 billion years old. In geological terms, this is recent. It is evidence that the geological processes responsible for exposing these materials were operating well into Pluto's maturity, not just during some brief, early phase of heightened internal heat. And yet, the deepest question that all of this raises, the question that separates what we know from what we strongly suspect, is whether the liquid reservoir responsible for the cryovolcanic activity near Right Mons and Virgil Fossé is a localized pocket of ammonia water solution trapped within Pluto's ice shell, or whether it is connected to something larger, a global or near-global subsurface ocean of liquid water at the boundary between the ice shell and the rocky core. The evidence that a subsurface ocean may exist beneath Pluto's ice is indirect but compelling. The most powerful argument comes from Sputnik Planitia itself. The basin sits within approximately 20 degrees of the longitude of Pluto's tidal axis, the line connecting Pluto's center to Charon. For a tidally locked body, this position corresponds to the minimum energy configuration, the place on the surface where a mass anomaly, a region that is heavier than average, would naturally come to rest as the body rotates and Charon's gravity aligns it. But Sputnik Planitia is a deep basin. It sits below average elevation. A basin below average elevation is a region where you have removed material relative to the surroundings, which should create a mass deficit, not a mass excess. The only way the basin can be both topographically low and gravitationally heavy is if there is something unusually dense beneath it, something that overrides the mass deficit of the missing surface material. The leading hypothesis for what that something is, a thinning of the ice shell directly beneath the basin, caused by the impact that created the basin, which allowed the subsurface ocean denser than the ice shell above it to upwell slightly toward the surface, creating an excess of mass that locked Sputnik Planitia into its current alignment with the tidal axis. If this interpretation is correct, the subsurface ocean is not a local pocket. It is a global layer surrounding Pluto's rocky core like the interior of a shell, and the basin is simply the place where the ice above it is thinnest. This interpretation was the dominant scientific consensus until 2024, when a paper by Ballantyne and colleagues published in Nature Astronomy offered an alternative. Using three-dimensional impact simulations, the Ballantyne team proposed that the alignment of Sputnik Planitia with the tidal axis could be explained without invoking a global ocean at all. If the impactor that created the basin was a rocky body approximately 730 kilometers in diameter and containing roughly 15% rock that buried its rocky core material beneath the basin's southern region, that buried rock, denser than the surrounding ice, would create exactly the mass anomaly needed to drive the tidal alignment, without requiring a liquid ocean anywhere in the system. This alternative model has not been ruled out. Both the ocean model and the Mascon model are scientifically plausible given the available data. Both make predictions that could in principle be distinguished by measurements of Pluto's gravitational field, the kind of measurements that an orbiting spacecraft could make by tracking its own orbital path as it passes over different regions and feels the subtle tug of the mass distribution below. But new horizons flew by. It did not orbit. It had no opportunity to map Pluto's gravity with the precision needed to distinguish between these two models. And until an orbiter returns an event that has not yet been funded, planned, or scheduled, the question of whether Pluto has a global subsurface ocean remains exactly where science is most uncomfortable, genuinely unresolved, with strong arguments on both sides and no definitive measurement available to arbitrate between them. What is not ambiguous is the geological record of activity. Cryovolcanic terrain exists at right Mons. Extensional fractures, consistent with an expanding, freezing interior, exist at Virgil Fosse and elsewhere across the surface. Ammonia compounds, young enough to have been recently exposed, are present at the surface. The nitrogen ice of Sputnik Planitia is actively convecting. Whatever the exact structure of Pluto's interior, something inside this world has been producing geological activity within timescales that are geologically young, and the evidence for that activity was collected from a flyby that lasted less than a full Earth day. There is another detail from the Sputnik Planitia convection story that deserves more attention than it typically receives. In 2021, research published in Nature by Morrison and colleagues proposed a mechanism for the convection in Sputnik Planitia that does not require internal heat at all, or at least, not primarily. The polygonal cell patterns in the nitrogen ice were shown to be consistent with a process driven by sublimation from the surface. Nitrogen ice at the top of the basin sublimates during the weak Plutonian day, carrying away mass and creating a density inversion that drives circulation in the deeper ice below. The Sun, even at Pluto's distance, even delivering only about 1/900th of the energy it delivers to Earth's surface, is still enough, barely, marginally, in the most efficient way possible, to drive this process in the unusually low viscosity nitrogen ice. If the convection of Sputnik Planitia is driven primarily by sublimation rather than by internal heat, that changes the interpretation somewhat. It means that the heart of Pluto's heart, the large bright plane at the center of Tombaugh Regio, may be responding more to its atmospheric and surface environment than to its deep interior. But it does not change the interpretation of the mountains, the fractures, or the cryovolcanic terrain. Those features require something from below. They do not sublimate into existence. The picture that emerges from 11 years of analyzing New Horizons data, from subsequent theoretical modeling, and from the JWST observations of 2025, is of a world that is thermally complex in ways that planetary science had not fully appreciated. For bodies of this size and distance, Pluto is not kept alive by one heat source. It is kept alive, to whatever degree it is alive, by the interaction of multiple contributing factors, none of them individually dominant, none of them individually sufficient, but together composing a thermal budget that has sustained some level of internal geological activity for far longer than the simplest models predicted. And hovering above all of that geological complexity, read in wavelengths of light that required the largest and most sophisticated space telescope in human history to detect, is an atmosphere full of organic chemistry, nitriles, hydrocarbons, complex carbon-bearing particles that is actively managing Pluto's climate from the top of the atmosphere downward, while the geological activity below manages it from the bottom of the ice upward. The haze in the deep interior, separated by kilometers of frozen shell and billions of years of isolation, are connected by a chain of chemistry and physics that has been running without interruption since the solar system was young. Understanding exactly what that chain carries, what passes from the rock to the ice, to the surface, to the sky, requires reading the atmosphere with a precision that only James Webb could provide. To understand what the James Webb Space Telescope actually did when it turned toward Pluto, you need to understand something about the nature of light that our everyday experience tends to obscure. When we talk about seeing something, we mean detecting the portion of the electromagnetic spectrum that our eyes evolved to process wavelengths roughly between 380 and 740 nanometers, the narrow band we call visible light. But the electromagnetic spectrum does not end there. It extends in both directions almost without limit, from the shortest gamma rays down through X-rays, ultraviolet, visible, and then outward into infrared, microwave, and radio wavelengths. Every object in the universe with a temperature above absolute zero emits radiation across a range of these wavelengths, and the peak of that emission is determined by the temperature of the object itself. Hot objects glow at shorter wavelengths, blue-white stars, glowing metal, the surface of the sun. Cold objects glow at longer wavelengths, deep in the infrared, where eyes cannot go and where most of the telescopes humanity built during the 20th century were blind. Pluto is cold. Its surface averages approximately -375 degrees Fahrenheit. Its atmosphere is colder still at the altitudes. Webb was measuring approximately -333 degrees Fahrenheit in the haze layers that MIRI was specifically designed to read. At those temperatures, the thermal emission from Pluto peaks in the mid-infrared at wavelengths between roughly 10 and 30 micrometers. This is not exotic physics. It is the same physics that makes night vision goggles work. The same physics that allows a heat-sensing camera to find a person hiding in darkness by detecting the infrared glow of a warm body against a cold background. The difference is scale and precision. A night vision camera designed for a battlefield needs only enough sensitivity to distinguish a human body at a few hundred meters. MIRI needed enough sensitivity to detect the thermal emission of a world 3 to 5 billion miles away, to separate that emission from the thermal glow of its moon, sitting only about 19,300 kilometers distant, and then to decompose the resulting signal into contributions from the surface, from the atmospheric gas, and from the solid particles floating in the haze, all simultaneously. The fact that this was achievable is a testament to the engineering precision of the instrument itself. MIRI is cooled to -447 degrees Fahrenheit within about 7 degrees of absolute zero to prevent its own thermal emission from drowning out the signals it is trying to detect. Without that extraordinary cooling, the instrument would blind itself with its own warmth. With it, MIRI can hear the whisper of heat from a frozen world at the edge of the solar system, and read in that whisper something that no instrument in history had managed to read before. The thermal light curves obtained by the MIRI imager in May of 2023, tracking Pluto's thermal emission at 4 wavelengths over multiple rotational periods, told the story of a surface with dramatically varying thermal properties from one region to the next. Sputnik Planitia, the great nitrogen ice plain, has an extremely high albedo. It reflects sunlight very efficiently, and its thermal inertia, a measure of how quickly a material heats and cools in response to changing illumination, is different from the surrounding water ice mountains and darker terrain. These differences are now quantified. Before the MIRI light curves, scientists had estimates for these properties derived from earlier space and ground-based observations. But those estimates carried large uncertainties because no instrument had successfully separated Pluto's thermal emission from Charon's at these wavelengths. Charon, tidally locked to Pluto and orbiting at approximately 19,300 kilometers, sits so close to Pluto on the sky from Earth's perspective that it falls within the same point of light detected by almost any previous instrument. Webb's angular resolution and sensitivity allowed the first clean separation, and the result was a set of surface thermal properties for both worlds individually, measured with a precision that established new quantitative constraints for every model of Pluto's energy budget going forward. But the finding that carried the greatest scientific weight, the one that confirmed a prediction made almost a decade before the observations were taken, was the detection and characterization of thermal emission from the haze itself. The haze particles are not just present above Pluto's surface. They are warm enough, relative to their surroundings, to contribute measurably to the total mid-infrared emission of the system. At 15 micrometers, the total flux from the Pluto-Charon direction contains a component that cannot be explained by the surface or the gas alone, an additional signal that, when modeled, matches precisely the contribution expected from a population of organic haze particles absorbing solar energy and re-radiating it as heat. This is the confirmation that the haze is thermodynamically active, not decorative, not passive, active, in the sense that it is absorbing energy from one source, the sun, and redistributing that energy in a way that fundamentally alters the temperature structure of the atmosphere below it. Ji Zhang, the UC Santa Cruz researcher, whose theoretical work in 2017 first proposed that the haze must be the dominant control on Pluto's atmospheric heat balance, noted, after publication of the June 2025 Nature Astronomy paper, that the confirmation of his predictions opened an entirely new set of questions about how haze particles function in nitrogen-rich, methane-bearing atmospheres across a wide range of planetary environments. The implications, he suggested, extend beyond Pluto to Triton, to Titan, and potentially to exoplanets with similar atmospheric compositions, worlds that orbit distant stars whose haze layers we have not yet been able to characterize with anything approaching MIRI's precision. Pluto, in this framing, is not just a subject of study. It is a calibration point, a world where we can test our theoretical models of haze atmosphere interaction because we have multiple independent datasets, new horizons, ground-based observations, and now Webb that constrain the system from different angles. The companion paper from the same observing campaign, led by Lelouch and published in April of 2025 in Astronomy and Astrophysics, pushed the analysis from thermodynamics into chemistry. Using the MIRI Medium Resolution Spectrometer, the MRS instrument, which disperses light into its component wavelengths, across the range from 4.9 to 27 micrometers, the team obtained what is essentially a chemical fingerprint of Pluto's atmosphere and haze, simultaneously, at spectral resolution high enough to identify individual molecular absorption and emission features. What the spectrum showed in the reflected solar component, shortward of about 8.5 micrometers, were the distinct spectral signatures of methane ice on Pluto's surface, specifically methane ice mixed with deuterated methane, which carries a hydrogen atom replaced by the heavier isotope deuterium, and a feature attributed to ethylene ice at around 10.4 micrometers. Ethylene, 2 carbon atoms bonded together with 4 hydrogen atoms, is one of the simple hydrocarbons produced when methane is broken apart by solar ultraviolet radiation in the upper atmosphere, and its presence as ice at specific altitudes records the history of that photochemical processing. These surface and near-surface signatures were new in terms of their spectral detail, extending the previous New Horizons compositional picture at wavelengths New Horizons instruments did not cover. But it was the haze signatures that captured the attention of astrobiologists and chemists working on the origin of life. Longward of roughly 11 micrometers, the spectrum transitions increasingly into thermal emission, and within that thermal component, the MRS data revealed spectral features from the haze particles themselves, emission and absorption structures consistent with complex organic material of the type described in the scientific literature as tholins, amorphous, polymer-like solids produced by energetic processing of simple molecules like nitrogen, methane, and carbon dioxide. The word tholin was coined by Carl Sagan and Bishun Kerr in the 1970s to describe the reddish-brown organic gunk they produced in laboratory experiments by irradiating mixtures of simple gases with ultraviolet light, electrical discharge, simulating what happens in the upper atmospheres of worlds like Titan. And though it was far less studied at the time Pluto, tholins are not a specific chemical compound. They are a class of material, complex, heterogeneous, poorly defined at the molecular level, but sharing the property of being built from simple precursors by energetic processing and containing carbon-nitrogen bonds, carbon-carbon bonds, and structural complexity that can, in the right chemical environment, serve as feedstock for the synthesis of biologically relevant molecules. The Webb MRS data also revealed specific nitrile ice features in the haze. Nitriles are molecules in which a carbon atom is triple bonded to a nitrogen atom, and they represent one of the most chemically significant classes of compound in the context of the origin of life. Hydrogen cyanide, the simplest nitrile, is a starting material for the synthesis of amino acids, nuclear bases, and other molecules central to the biochemistry of every living thing on Earth. More complex nitriles, like acetonitrile and propionitrile, have been detected in the interstellar medium, in cometary comas, and now in the atmosphere of Pluto. Their presence in the haze, as solid-phase ice particles condensed at the cold temperatures of Pluto's upper atmosphere, means they are not ephemeral gas-phase species that will rapidly escape to space. They are being captured and stored in solid form, raining down slowly through the atmosphere to eventually settle on the surface below. The second JWST Pluto paper also identified hydrocarbon ices in the haze spectrum, including features consistent with compounds like diacetylene and possibly cyanoacetylene molecules that have also been detected in Titan's atmosphere, and that represent further products of the complex photochemical cascade operating in Pluto's upper atmosphere when solar ultraviolet light breaks methane and nitrogen apart, and the fragments recombine into progressively more elaborate structures. The entire system functions like a molecular construction kit operating in slow motion over geological time, assembling increasingly complex organic structures from the simplest available raw materials: nitrogen gas, methane gas, traces of carbon monoxide, and the ultraviolet photons arriving from the distant sun. The connection that Xi Jiang drew after the publication of the June 2025 paper, the one concerning Earth's early atmosphere, deserves to be examined with care, because it is genuinely important and genuinely careful science at the same time. About 2.4 billion years ago, a biological revolution fundamentally changed Earth's atmosphere. Photosynthetic organisms began releasing oxygen as a metabolic waste product at rates that eventually accumulated to the point where free oxygen became a significant atmospheric component. Before that event, known as the Great Oxidation Event, Earth's atmosphere was reducing rather than oxidizing, dominated by nitrogen, methane, water vapor, carbon dioxide, and traces of hydrogen, without significant free oxygen. The chemistry of that pre-oxygen atmosphere was, in its broad outlines, not entirely unlike the chemistry of Pluto's atmosphere today. Nitrogen dominated, methane bearing, receiving ultraviolet radiation from the young sun and producing complex organic compounds in the upper atmosphere that rain down onto the surface below. On early Earth, that atmospheric organic chemistry happened in an environment that also included liquid oceans, hydrothermal vents at the ocean floor, where water interacted with hot rock and emerged enriched with minerals and chemical energy, and geological processes that continuously cycled material between the surface, the ocean, and the deep interior. Life arose in that environment. We are the descendants of whatever chemistry crossed the threshold from complex organic molecule to self-replicating system in those conditions. The crucial distinction is that early Earth had all of these features together simultaneously in a geochemically vigorous planet with an active mantle, a vast liquid ocean, and proximity to a warming sun. Pluto has some of these features: complex organic chemistry in its atmosphere, a potentially liquid interior at the core mantle boundary, but it lacks others. The organic particles settling from Pluto's haze onto its surface are burying themselves in nitrogen ice and methane frost, rather than dissolving into a warm, geochemically rich ocean. The hypothetical liquid water at the core mantle boundary, if it exists, is separated from the organic chemistry above by tens to possibly hundreds of kilometers of ice, with no obvious pathway for efficient chemical exchange between the two reservoirs. This does not mean the chemistry is irrelevant. It means the specific conditions required to connect the organic chemistry to a liquid water environment are more constrained than on early Earth, and that those connections, if they exist at all, are far harder to observe from the outside. What the Webb observations establish, with the authority of peer-reviewed measurements, is that the chemical ingredients are present, the building blocks are being assembled. The raw materials that, on Earth, preceded the chemistry of life by hundreds of millions of years are floating above Pluto's surface in measurable, quantifiable concentrations, being synthesized continuously by the same photochemical processes that have been operating since the solar system formed. Whether those ingredients can ever be combined in the right way, in the right environment, to do something biologically interesting is a question that no telescope can answer. It requires in situ investigation, a spacecraft that can sample the atmosphere, analyze the surface composition at multiple locations, and probe the interior with radar and gravity measurements. It requires, in short, going back. There is a broader context for the Webb observations of Pluto that becomes even more significant when you pull the camera back from this single world and look at what else the telescope has been finding in the Kuiper Belt. In 2024, JWST observations of Eris and Makemake, two of the largest known dwarf planets, both residing in the Kuiper Belt, alongside Pluto, revealed spectral signatures that the researchers involved interpreted as potentially consistent with geological activity. Eris, whose diameter is approximately 2,326 kilometers, making it comparable in size to Pluto, was found to have surface methane ice that appeared more isotopically uniform than expected for methane that has simply sat on an ancient, radiation-processed surface for billions of years. Without refreshment, the methane on Eris looks young. Not young in the sense of millions of years, young in the sense of potentially being continuously replenished from the interior, possibly through outgassing or slow geological processes that bring fresh material to the surface before it can be significantly altered by space radiation. Marker, slightly smaller than Eris, at approximately 1,430 kilometers in diameter, showed similar hints of fresh or recently processed surface material in its Webb spectral data. The scientific community's reaction to these findings was appropriately cautious. The lead researcher Mike Brown of the California Institute of Technology, who has studied Kuiper Belt objects extensively, noted that the evidence for geological activity in Eris and Marke is significantly more indirect than the evidence for activity at Pluto, and that only dedicated missions visiting these worlds could definitively resolve the question. But the pattern is striking. The three largest known Kuiper Belt dwarf planets, Pluto, Eris, and Marke, all show evidence at some level of surface freshness or chemical complexity that is not obviously consistent with a completely dead, radiation-processed surface, frozen for the entire age of the solar system. If even one of these worlds is geologically active, it might be an anomaly. If all three are showing similar signals, it begins to look like a systematic pattern, like geological vitality in small icy outer solar system bodies, might be more widespread than any pre-New Horizons model predicted. The implications of that systematic pattern extend far beyond our own Kuiper Belt. Astronomers have now confirmed the existence of thousands of exoplanets, planets orbiting stars other than our Sun, and statistical analyses of the planetary populations detected by missions like Kepler suggest that outer, icy bodies are extremely common around other stars. Many planetary systems appear to have significant populations of small icy worlds at large orbital distances, analogous to what we find in our own Kuiper Belt. If those worlds are maintaining geological activity driven by the same combination of radiogenic heating, tidal interactions, insulating clathrate layers, and ammonia antifreeze chemistry that appears to be operating inside Pluto, then the number of potentially geochemically active environments in the galaxy, environments where complex organic chemistry might be occurring in liquid water reservoirs deep beneath the ice, is not a small number. It could be very large. The habitable volume of the cosmos, if these ideas are correct, extends far beyond the thin rings of space around stars where liquid water can exist on planetary surfaces. It reaches into the interiors of small, dark, cold worlds parked at the outer edges of solar systems across the galaxy. Worlds we would never look at twice if we judged them solely by the light arriving at their frozen surfaces. The Webb results from 2025 have not answered the question of whether Pluto is habitable, or whether it ever was, or whether it ever will be. What they have done is something more foundational. They have confirmed that the chemical complexity we associate with habitable environments is not restricted to the inner solar system. The organic chemistry is there. The heat sources capable of maintaining liquid water at depth are there. The geological processes forcing fresh material from the interior to the surface are there, recorded in the texture and composition of terrain that should, by every pre-New Horizons calculation, be frozen and inert. And the telescope that read all of this in wavelengths of light invisible to every previous instrument is now looking at other Kuiper Belt worlds, extending the inventory, mapping the territory of a region of space that we have barely begun to explore. What Webb started is not the answer. It is the clearest and most precise articulation yet of the question. And the question is larger than Pluto, larger than the Kuiper Belt, larger than our solar system. It is the question of where, in the universe, chemistry becomes complicated enough to matter, and whether the places where that happens are as rare as we once assumed, or as numerous as the frozen worlds drifting in the dark at the edge of every star's domain. To answer, it requires something no telescope, however powerful, can provide. It requires a return visit. It requires an orbiter. And what that orbiter could find, and what it would mean for everything we think we understand about life in the universe, is where this story has been building from the very beginning. There is a particular kind of scientific mistake that is more difficult to correct than the ordinary kind, because it does not arise from bad data or careless measurement. It arises from a failure of imagination dressed up as a reasonable inference. In the history of planetary science, this kind of mistake has been made repeatedly and consequentially. The assumption that what we observe closely must represent what we would find everywhere if we looked. We surveyed the inner solar system and found that geological activity required mass. The larger the world, the more active its geology. We surveyed the moons of the outer planets and found that activity required proximity to a gravitational giant Io erupting constantly from Jupiter's tidal forces, Enceladus geysering from Saturn's. We built a mental model in which geological vitality was a privilege reserved for worlds that earned it through size or situation, and we applied that model to the small, cold, distant bodies of the Kuiper Belt with a confidence that turned out to be wholly unwarranted. Pluto has spent 11 years dismantling that model piece by piece, line of evidence by line of evidence, with the patience of a world that has been doing the same things in the same dark for 4.5 billion years without requiring anyone's permission or acknowledgement. New horizons arrived and found mountains of water, ice that should not exist, a convecting nitrogen sea that should have frozen stiff, fractures in the crust, consistent with an interior expanding as it freezes, and terrain resurfaced by cryovolcanism within the last billion years. The James Webb Space Telescope arrived years later and found that the haze above all of this is made of complex organic chemistry, is actively regulating the atmospheric temperature, and contains the molecular precursors of biologically relevant compounds, raining slowly down from the sky onto a surface that is anything but the barren, radiation-blasted archive the old models predicted. What does it mean to have been this wrong about a world for this long? The answer is not simply that we need to correct the textbooks. The answer is that we need to examine the reasoning that led to the error, because that reasoning is still being applied right now, today, to thousands of other bodies we have never visited, in our own solar system, and across the galaxy. We are still assuming that small means dead. We are still assuming that cold means finished. We are still building models of planetary habitability that treat the surface of a world as the relevant environment and the star's energy as the essential fuel, when Pluto is sitting 4.5 billion miles away, telling us, with all the geological eloquence at its disposal, that neither of those assumptions is reliable. The case for reconsidering the definition of a habitable environment begins with the recognition that liquid water the single physical requirement that most astrobiology frameworks treat as non-negotiable does not require a star. It requires heat from any source, combined with chemistry that depresses the freezing point sufficiently to maintain the liquid phase under the available thermal conditions. Both of those requirements can be met in the interior of a small icy world far from any star. Radiogenic decay provides the heat. Ammonia provides the freezing point depression. Clathrate hydrates provide the insulation that keeps the system from dissipating its energy too quickly. None of these mechanisms depend on proximity to a sun. All of them are available to small icy bodies distributed throughout the outer solar system and, by implication, throughout the outer regions of every planetary system in the galaxy. This realization forces a quantitative revision to the concept of the habitable zone that is difficult to fully absorb. The classical habitable zone is a ring around a star, the region where the stellar energy flux is sufficient to maintain liquid water on the surface of a world with an Earth-like atmosphere. For a Sun-like star, this ring extends from approximately 0.95 astronomical units to roughly 1.7 astronomical units from the star, and it contains, in our solar system, primarily Earth. This zone has been the organizing framework for the search for life around other stars for decades. Missions like Kepler and TESS have been specifically designed to identify planets orbiting within this zone, on the assumption that a planet in the habitable zone is a planet worth investigating further. But the habitable zone is defined entirely in terms of the surface. It says nothing about the interior. And if liquid water can be maintained in the interiors of small icy bodies through internal heat sources rather than stellar radiation, then the habitable volume of a planetary system is not a ring. It is a sphere or something more complex than a sphere, following the distribution of icy bodies throughout the system that extends from whatever distance allows surface liquid water all the way out to the furthest point where an icy body can maintain an internal liquid layer above its core. In our solar system, that outermost boundary is not the outer edge of the asteroid belt, or even the orbit of Jupiter. It is currently unknown because we have never looked carefully enough at the Kuiper belt, or the even more distant scattered disk, to know where the geological activity stops. Pluto is at 39.5 astronomical units. Eris spends part of its eccentric orbit nearly 100 astronomical units from the Sun. The evidence from Webb and from New Horizons suggests that at least some of these objects may be geologically active. The implications for the number of potentially habitable environments in the galaxy are staggering in their magnitude. There are an estimated 100 to 200 billion stars in the Milky Way alone. Most of them are expected to have outer icy body populations analogous to our Kuiper belt, based on the theoretical models of disk evolution that produced our own solar system structure. If even 1% of those systems contain outer icy bodies maintaining active liquid water interiors, the number of potentially habitable interior environments in the Milky Way is many billions, far exceeding the number of planets estimated to occupy the classical habitable zones of their host stars. This does not mean life exists in all of them or any of them. It means that the inventory of places where the physical prerequisites for life are met is almost certainly vastly larger than any calculation based only on surface habitability has ever suggested. The question that follows is one of access. Even if life arose in the interior of a Kuiper belt body, in a subsurface ocean sealed beneath kilometers of ice, with no connection to the surface and no means of exchanging material with the space environment, that life would be permanently isolated. It could not spread, it could not signal. It would be unknown and unknowable without a spacecraft capable of reaching the surface, penetrating the ice, and accessing the liquid below. This is the limitation that makes the potential biological significance of outer icy bodies simultaneously profound and profoundly difficult to act upon. We know how to detect biosignatures in planetary atmospheres around distant stars, or at least we know what signals to look for and are building the instruments to detect them. We know how to analyze the surface composition of Mars or the plumes of Enceladus with in situ instruments. We do not yet know how to probe the interior of a Kuiper Belt body from a passing spacecraft, and we do not have and have never had an orbiter around Pluto. That last fact is worth sitting with for a moment because it is genuinely remarkable given everything that Pluto has told us. We have sent spacecraft to orbit every planet in the solar system except the two most distant, Uranus and Neptune, and we have sent orbiters to Mars, Jupiter, Saturn, and even the dwarf planet Ceres in the asteroid belt. We have landed rovers on Mars and probes on Titan and the surface of Venus and multiple asteroids and comets. But Pluto, a world that knew horizons, proved to be one of the most geologically and atmospherically complex bodies in the outer solar system, a world that the James Webb Space Telescope has now confirmed to be producing complex organic chemistry in its atmosphere and to have surface properties that demand a liquid water interior explanation Pluto has never had anything in orbit around it. No spacecraft has mapped its gravity field. No instrument has measured its magnetic environment continuously over a full orbital period. No radar has penetrated its ice shell to look for reflections from a hypothetical subsurface ocean. We have one flyby and a handful of years of Webb observations, and from those alone, the science is extraordinary. The proposed Persephone mission, a Pluto system orbiter and Kuiper Belt Explorer concept developed by Carly Howitt and colleagues at the Southwest Research Institute, would be the next step. The estimated cost at the time of the concept study was approximately $3 billion, not including launch costs. That is the same order of magnitude as the Europa Clipper, which is currently en route to Jupiter's moon Europa to investigate its subsurface ocean. The Planetary Science Decadal Survey, the document that guides NASA's priorities for planetary exploration over a decade, identified a Uranus orbiter and probe as its top flagship mission priority for the period 2023 to 2032, and the Enceladus orbiter and lander as the second. A Pluto orbiter did not make the top tier in the most recent survey, in part because the scientific community recognized that Uranus has received far less attention than the other giant planets, and its exploration was arguably more urgent from the standpoint of understanding ice giant formation. But the Pluto case is building. Every new result from Webb adds to it. Every new geological analysis of New Horizons data adds to it. Every new paper on the thermal evolution of Pluto's interior, weighing the ocean model against the Mascon model, and finding that the ocean model remains strongly supported, these all add to the case for a return. The question of whether Pluto has a subsurface ocean cannot be resolved from Earth. It cannot be resolved by Webb. It requires a spacecraft that can measure the gravitational field of Pluto to sufficient precision to distinguish the density distribution of an ocean-bearing interior from that of a solid one. It requires ice-penetrating radar to image the structure of the crust from above. It requires an instrument that can sample Pluto's thin atmosphere directly, measure the ratios of isotopes in its nitrogen and methane, and determine how those ratios have evolved over time as a record of atmospheric escape and interior outgassing. It requires, in other words, the full suite of measurements that only an orbiting spacecraft can provide. And there is one additional measurement that an orbiter could make that no flyby and no telescope will ever be able to provide, and whose importance has grown with each new Webb result. If Pluto's cryovolcanic activity is ongoing, if the right Mons terrain is still being modified today, or even within the last tens of millions of years, then the material being extruded from the interior onto the surface carries chemical information about the deep environment that it came from. That material has been in contact with the rocky core. It has had access to whatever heat and mineral chemistry the core provides. It has potentially passed through the liquid water zone, if one exists, on its way from depth to surface. An orbiter equipped with a mass spectrometer, a near-infrared spectrometer with higher resolution than New Horizons carried, and a surface camera with spatial resolution sufficient to distinguish individual geological features at meters scale, could analyze the composition of fresh cryovolcanic deposits and ask, what did these materials encounter on their way up? Do they carry the signature of water-rock interaction? Do they contain the specific organic molecules associated with hydrothermal chemistry? Do they contain anything that would be anomalous in a purely abiotic geological system? These questions cannot be answered from 4.5 billion miles away. They can only be answered by something close enough to smell the terrain, metaphorically speaking, and that something does not yet exist in any concrete mission plan funded for construction. The deeper philosophical reckoning that Pluto demands is not simply about expanding the definition of where life could exist, or about revising the list of solar system bodies worth sending missions to. It is about the systematic nature of the error we made. Pluto was not one world that we happened to underestimate through some specific lapse of attention. It was representative of an entire category of object, small, cold, outer solar system body that we dismissed as a class, without adequate justification, on the basis of models that we did not test rigorously enough before we trusted them. How many other categories of object have we dismissed in the same way, with the same level of uncritical confidence? How many other places in the universe are doing things we have decided they cannot do because our models said they should not? The history of astronomy is, in one reading, a history of this kind of mistake being made and corrected on progressively larger scales. We assumed the Sun was unique and discovered it was one of hundreds of billions. We assumed the Milky Way was the universe and discovered it was one of trillions of galaxies. We assumed planets were rare and discovered that most stars have them. We assumed the classical habitable zone was the relevant domain for life and discovered that the actual chemical complexity of the universe extends far beyond any star-centered ring. Each correction has been in the same direction. The universe is larger, stranger, and more hospitable to interesting chemistry than we thought. And the things we were most confident were impossible have a way of turning out to be merely unfamiliar. Pluto is not the last example of this pattern. It is the most recent and the most precisely documented, thanks to the most powerful space telescope humanity has ever built. The MIRI instrument on James Webb read the chemical signatures of complex organics in the haze of a world that 9 generations of astronomers assumed was geologically finished, and confirmed with the precision of peer-reviewed spectroscopy that the chemistry of life's antecedents is present in one of the coldest, darkest, most remote corners of our own solar system. What that means for the search for life is not that we should immediately declare Pluto a candidate, habitable world. The scientific community is right to maintain the careful distinctions between confirmed observation, strong interpretation, candidate explanation, and speculative reconstruction. The ocean is not confirmed. The cryovolcanism is not confirmed as ongoing. The organic chemistry in the haze is not confirmed as connected to any liquid water reservoir. Each of these points requires additional evidence, and generating that evidence requires returning to Pluto with instruments designed to answer the specific questions that New Horizons and Webb together have raised. The science is not finished. It has barely started. What the evidence does mean is that we can no longer say, with any intellectual honesty, that Pluto is probably irrelevant to questions of life in the universe. That statement, which was essentially the consensus view as recently as 20 years ago, has been falsified by direct measurement. Pluto is not confirmed relevant to those questions. Either the evidence does not yet support that, but the space between probably irrelevant and certainly relevant is where the most important science always lives. And Pluto now occupies that space with more justification than almost any other body in the solar system, beyond the classical ocean world candidates of Europa and Enceladus. The Kuiper Belt contains an estimated 100,000 objects larger than 100 kilometers in diameter. Of these, we have visited 2 Pluto by New Horizons in 2015 and Arrokoth by the same spacecraft in 2019 on its extended mission. We have obtained detailed spectroscopic data on a small handful of the largest objects with Webb. For the vast majority of Kuiper Belt objects, we know nothing beyond their orbital parameters and rough estimates of their size derived from how much light they reflect. We do not know if they are geologically active. We do not know if they have atmospheres. We do not know if they contain liquid water. We do not know if they have produced complex organic chemistry on their surfaces or in their interiors. We assumed they were all frozen and dead, and we stopped asking questions. Pluto has told us that assumption was wrong, at least for one world and probably for more. Eris and Makemake are providing hints in the same direction. The universe at the outer edges of our solar system is not the graveyard we thought it was. It is a vast, inadequately explored territory full of small, dark worlds that may be quietly doing something extraordinary in their frozen interiors, producing the chemistry of complexity in environments that receive almost no light from the nearest star, sustained by heat sources that have nothing to do with the sun whatsoever. We wrote off Pluto for 96 years. We are probably writing off most of the Kuiper Belt right now, today, for the same reasons. The geological evidence says we should stop. The atmospheric chemistry says we should stop. The James Webb Space Telescope, with its MIRI instrument reading the infrared signatures of organic complexity floating in the haze of a world billions of miles from anything we previously thought of as a heat source, says we should stop. The greatest obstacle to finding life beyond Earth has never been distance. Voyager 1 is more than 23 billion miles from Earth and still sending data. New Horizons reached Pluto after 9.5 years of travel. The James Webb Space Telescope is operating right now, reading the chemistry of the solar system in wavelengths we could not access a decade ago. Distance is an engineering problem, and engineering problems yield to engineering solutions, given sufficient time and funding and will. The obstacle that has cost us the most has been assumption, the quiet, confident, unexamined assumption that small means dead, that cold means finished, that far means irrelevant. Pluto does not know about these assumptions. It has been doing what it does, convecting its nitrogen sea, fracturing its ice shell, extruding material from depth to surface, building complex organic chemistry in its atmosphere for 4.5 billion years, regardless of whether anyone was looking. For 96 of those years, a dot moving on a photographic plate was all we could see. For 11 of those years, a flyby's worth of data has been slowly rewriting everything we thought we knew. For the last few years, the most sensitive infrared instrument in the history of space exploration has been reading the chemical signature of what floats above that surface and finding that it is not simple, not inert, not finished. We do not know if there is life on Pluto. We do not know if there ever was. We do not know if the ocean we suspect exists beneath the ice is real or an artifact of a frozen rocky mascon mimicking its gravitational signature. We do not know if the cryovolcanism is still active or has entered a quiet phase from which it may or may not emerge. We do not know, because we have not looked closely enough for long enough with the right instruments in the right places. What we do know is that the world Clyde Tombaugh found moving in his blink comparator on that February morning in 1930 is not the world anyone thought it was. It is stranger than the models predicted, more active than the physics suggested, more chemically complex than the instruments of the era could detect, and more important to the question of where life can exist in the universe than 96 years of comfortable assumption ever allowed us to imagine. We were wrong about this world. The only honest question left is how wrong, and the only way to find out is to go back. Sleep now, wanderer. Even the dark edges of space are keeping their secrets warm.